Okay. Hello, everybody, and welcome to the event Women for Space. I'm Monica, a member from WIA-E Barcelona, and I would like to present today's speaker, Sara Correyero. Before that, I would like to mention our next event, Space for Change, which will be the next 20th of January at 6:30 with Vanessa Del Campo. She will explain how she has brought her two passions, space and movies, into her professional career. The title of the speech is Mars, Oman, and Moon Diary, Space Exploration in Easy Film. Don't miss the next Space for Change. And today, in this event of Women for Space, Sara Correyero will present Athena, and it's a special electrical propulsion system for nanosatellites. Sara is an aeronautical engineer and has a PhD in fluid mechanics from the University Carlos III de Madrid. Currently, she is the operational director and responsible for the testing in DNI Space. So who better than she to explain us the new technology of this electrical propulsion? And many thanks, Sara, for sharing with us the project which you are working on, and many thanks for making possible events like this one of Women for Space, for example. And if some of the audience have some questions to do, you can write it down in the chat and during the presentation, and we will manage them after Sara's talk. Thank you and enjoy the presentation. You can start when you wish, Sara.
Okay, Monica, thank you very much. It's a pleasure to be here today and to share with you all our developments that we are doing at DNI Space. Also, because we are a very young company, we only have 2 years of life, so for us it's really a big opportunity to be able to really explain and to share with you all what we are doing at DNI. So I'm gonna share my screen now. Okay. Can you see my screen properly?
Yes, we can see it. If you can make it,
great.
Yes, now it's completely presented. Yeah, thank you.
Perfect. Okay, so as Monica was saying, like I'm the COO and co-founder of DNI Space. We are a company here located both in Madrid and Barcelona, and we are we have developed Athena, which is the first Spanish electrical propulsion system for nanosatellites. So today in this talk, I will explain how has been the process of developing Athena, how have we build, test, and qualify this propulsion system, and I will also share with you what's our mission at DNI Space and what do we plan to do in the next months and in the following years. No, because I always like to start with the slide, because when people ask us like what do you do at DNI Space? No, I always say like we are a rocket company. No, we are a propulsion company. But when we think about propulsion, normally people think about the image that you see at the left, no? The typical launcher rocket propulsion system. And we are not this kind of company, or not at the moment. Well, the propulsion system that we developed are more similar to the things that you see at the right, which is actually in the micro scale. So we do, let's say, micro propulsion systems. And when we say micro, it's really in the micrometer scale. So here you can see actually how our propulsion system looks when we look them at the microscope in the micro scale. No? And actually here, you can see a picture of what has been Athena Pie, which is what I'm going to also to talk today, which is our first, let's say our first prototype, our first flight model, which is based on electrospray technology. And you can see the size of the rocket. No, it's really small propulsion system, which fits on directly on your hand. No? So why do we need propulsion? We always say like propulsion is not nice to have, no? And I think like we are all aerospace engineers, we are, this is something that we all know, that propulsion, it's a need, it's completely a need. And you can see, I mean, one of the reasons that I say this is when you go to larger platforms as microsatellites or small satellites, no? or even more larger platforms, they always carry onboard propulsion. But in the nanosatellite class, nowadays, only the 6% of the nanosatellites which have been launched have historically carried onboard propulsion, which is really something that we want to change, no, at DNI Space. Obviously, the nanosatellites are so small that they have a lot of restrictions. But for what let's say these small satellites can use onboard propulsion. Well, one of the main, let's say, use cases is, for instance, like drag compensation. These small satellites fly in very, very low Earth orbit, so they need propulsion to compensate the atmospheric drag that is in that they have, no, in order to be able to stay at their orbits. Then also one of the main cases is what we call like constellation deployment. So basically we launch all the satellites in the same launcher, and then we use propulsion to, let's say, deploy the constellation in the place where we want it to be exactly. No, obviously we think of more ambitious things, so like, for instance, like formation flying or deep space missions. We definitely need propulsion systems. No? So I like a lot to put this video. I think it's pretty cool. And I'm sure that you all are familiar with it. This is the Starlink constellation from Elon Musk. You know, I think it's a very, let's say, obvious use case for onboard propulsion. No, here you can see how they launch basically what I was saying before. No, they launch all the satellites in what it's called a rideshare launch, so in the same launcher, and then they use this propulsion to really deploy the constellation. No, here at the right you can see a video which is real, how the constellation looks like from Earth, which is, I think it's really, really amazing. No? So what we do at DNI Space, we basically have two strong, let's say, technology developments, which we are developing in parallel. Our, let's say, electropropulsion systems, as they are, you can see at the left. Here also you can see one of our prototypes. It's a very, very high efficient and high performance. The most important thing, custom electric propulsion systems. I will explain a little bit more in detail why it's completely custom. And then on the right, you can see we also developed, let's say, in-depth mission analysis for mission plannings and maneuvers optimization. So we believe that this basically the design of the propulsion system must be done in parallel and taking into account with the mission requirements from the beginning. No, so we do this. We have this concurrent engineering approach. So basically, we tell our clients, hey, what's your satellite platform looks like? No, how's your satellite platform looks like? What mission do you want to carry? And then we design the propulsion system that really fits with these requirements. No, so this concurrent engineering approach. I also like a lot to put this sentence here, which basically says like, well, we believe that clients should not be forced to build a spacecraft around a small number of available propulsion products, but that this system should adapt to the constraints and requirements of each individual mission. So this is exactly like our vision for the onboard propulsion. We believe that clients should not decide like between, okay, should I carry a 10 watts, 20 watts, or a 50 watts propulsion system with different performance, different specific impulse and thrust. But this is something that us, like the propulsion engineers, should do, no, for our clients. So we basically, like I was saying, we take into account platform, take into account the mission, and we design a completely customized propulsion solution. So this is what we do. We, as I was saying, we all, and also all or most of our competition do the things the other way around. They try to feed the propulsion systems in different satellites and in different missions, and we are like doing the things in the like with the other perspective. No. So let me present you to Athena, which is what I'm going to talk today. Athena stands for adaptable thruster based on electrospray for nanosatellites. Here you can see a render on the right, and it basically has, like, let's say, two main or characteristics. No, the first one is that it's fully scalable. As you can see here, it's based on a modular approach. So you can imagine, no, we put more, let's say, chips or more of these stacks if our client needs more thrust, for instance, like we completely customize the number of thruster stacks that we need to incorporate in the propulsion system. And it's a software, we say it's a software-defined thruster, which is a little bit abstract concept that basically means that we design the propulsion system taking into account, as I was saying, all the maneuvers optimization from the beginning. No? So our technology, Athena, as I was saying, is based on Electrosprays. Electrosprays is an electric propulsion technology, which is, but it's not a plasma propulsion technology. Okay, it's based on the extraction and acceleration of ionic liquids, which are basically molten salts. Like you can imagine, you have like negative and positive molecules all in a liquid, and we use electrostatic fields to extract these positive and negative ions and accelerate them outside of the spacecraft. No? This kind of technology, Electrosprays, it started to be developed in the United States in the 60s, in the MIT actually, and but it hasn't been like commercialized yet, since well, it has quite a lot of, let's say, engineering challenges that we are trying to solve at DNI Space. But it's very, very, very interesting for small satellites. No, one of the reasons, well, first of all, as I was saying, the fact that we have ionic liquids and not other kind of let's say pressurized deposits means that we are going to have a very, let's say, very dry. Very significant dry mass reduction, and we don't need to use any valves or flow controllers, which is a huge advantage. We also have, let's say, our acceleration is purely electrostatic, so we don't have any magnetic elements, which means that we also have further mass and power reductions, and we can have net zero current without the need of a cathode, which is also a huge advantage for this electric propulsion technologies. And one of the most important things is that we are able to retain very high efficiencies at very, very low power. When I say very low power, I mean normally we have the prototype that we have at the moment needs less than 1 watt of total power, so it's really very, very low power. So here you can see a schematic of how our technology works. Basically, what we do is we apply, let's say, a very high voltage between the extractor and the what we call the emitter, which is the first two pictures that you can see at the left. This will be like the extractor, and the second one will be the emitter. No? So we apply a very high voltage between these two, and our propellant, which is, as I was saying, an ionic liquid, which is stored in 3D printed porous deposits, will basically reach the tip of the cone when we apply this high electric field. And here, which is where the electric field is higher, the highest concentration of electric field, the molecules will be extracted and accelerated outside of the spacecraft. So this is how, well, very obviously a very simple schematic of how this technology works. The greatest challenge related to this technology is related to the manufacturing, as you can imagine. Like we use microfabrication and nanofabrication techniques in order to have, let's say, the optimal configuration of this technology. And this is where like we are putting like also, let's say, most of our resources at the moment. So I will also, before I get into how we build, let's say, test and qualify our first prototype, Athena Pie, I would also like to introduce you to Enigo. Since I was saying, like at ENI, we have this, let's say, we are developing these two technologies in parallel because we believe that they must be done like with a concurrent engineering, with a concurrent engineering approach. Enigo, which is it's a free software that you can actually access through our website at DNI.space. And it's basically, for us, it's a completely lead generator. No? So what's the main goal of Enigo? Enigo basically allows you to design and optimize your propulsion system, taking into account both your requirements from your satellite platform and from your mission. So I will show you now a little bit how it works. It's powered also by artificial intelligence, and it has been benchmarked against industry standards as GMAT, for instance. No? So it basically allows for concurrent mission and propulsion system design. So this is how our software looks like. Also, I will really recommend you to play a little bit with our software, and please give us feedback because now it's currently it's in the beta version, let's say. So we are also looking for this feedback from all the users. But basically, you will select, for instance, the kind of platform that you have here. You can see you have a 3U satellite CubeSat. You will say, okay, in thruster envelope, you can select, okay, how much power I'm willing to give to the propulsion system. No, for instance, here you can see it's marked in 20 watts. And you also will select like the initial orbit. No, so where is the launcher going to leave you? Imagine here the launcher, for instance, will leave you at 500 kilometers. No, just as an example. So then you will select the missions. Then you will say, okay, what do you want to do? I want to do an orbit transfer, round facing, the orbiting. And you will say, for instance, here you can see an orbit transfer maneuver. So you will say, okay, I want to change my inclination like 5 degrees, no? Also, you can select like the maximum maneuver duration, because normally this is also a constraint for the clients to say, okay, how many days, no? What's the maximum days that I can allow the let's say the propulsion system to or what's the maximum maneuver duration, no? And here you will have, well, you will see the maneuver results. And then finally, this will be like the output of our software, which is also, I would say, it's a very, very fast tool. So you will see in basically seconds, you will have this kind of results. So you can see, for instance, here, this is an example that we were doing 3 different maneuvers, around facing, in orbit transfer, and the orbit. And you can see the total thrusting time, the propellant that we have used, the amount of propellant, in this case, 143 grams, and the thruster power and the total delta V. No? And one of the most interesting also outputs of this software is that you could potentially download directly the CAD of our propulsion system, our Athena thruster, that will be completely customized for this specific mission that you have selected. No? So this is, let's say, Enigo is this fast tool that for us is a completely lead generator. It also allows us to show to the industry what are our capabilities in terms of mission analysis. But we also have, let's say, a proprietary mission, more in-depth mission analysis tool, which is called ENI 360, which has, let's say, higher fidelity. It's more robust and versatile, and it's run in Amazon Web Services. And well, it has basically much more complex constraints, no? As you can see here in my slide. So we use this ENI 360 basically to perform more in-depth mission analysis for different companies. So what do we do at DNI Space? We have this is our, let's say, our main capabilities. As you can see here, we develop electric propulsion systems. We have this mission analysis capabilities. We also have we do microfabrication, micro and nanofabrication. We have experts in the field. In this sense, I would say that we have a very strong collaboration with the CNM of Barcelona, actually, from the TESIC, which is one of our main partnerships, because obviously this manufacturing techniques, they require very precise machines and very, let's say, specific, no? The manufacturing techniques. We also have the capability of qualifying some of our propulsion systems. I will explain a little bit more how we qualify these systems and how we test them. And as we say, always, like, our main vision or our main business proposition is maneuvering service. No, it's not only like providing the propulsion solution, the propulsion system, sorry, but also like providing all the trajectories and all the maneuvers optimization, no? Like propulsion and maneuvering as a service. So this is our team at the moment. We found the company in 2019, Mick, Daniel, and me. And currently we are 12 people in the company. Well, actually 13, 13, almost 14. We will end the year with 14 people. You can see we have engineers, let's say propulsion engineers, mission analysts, let's say electrical engineers, microfabrication specialists, obviously. And we are part, and we belong to the European Space Agency Business Incubation Center at the moment. And we have our main partnerships are currently with the University Carlos III de Madrid, which is where the 3 of the co-founders of DNI Space, we did our PhDs there. And with the CNM of Barcelona, which, as I was saying, it's our, let's say, strongest partnership, which is related to microfabrication. So this year has been a quite very good year for us too, because we have been, our idea and our main, let's say, business proposition has been recognized in several competitions, as you can see here. Some of them we were recognized with the best technological business idea from the community of Madrid. We were also finalists in the Shenzhen Innovation Entrepreneurship and Innovation competition this year. We won the Industry 4.0 vertical in South Summit also this year, so we were quite happy. And very recently we have been selected as one of the top 10 startups in Spain, which is by the journal El Referente, and basically one of the, let's say, best 10 startups in Spain. Also, we are also very, very happy for that. So now I'm going to tell you, like, let's talk a little bit more about our technology, about Athena, and as always, well, it has been sent in the news and also at our social media. We are going to space. We are very happy because now in January 2022 we are launching our first propulsion system, which has been integrated in a PocketSat. And for us, it's a great opportunity because it will allow us basically to test our technology in orbit, to try to ignite, to see if everything works as it should. So we are very, very happy for this. No? So now I'm going to explain you in the next minutes, in the second part of the talk, how we actually built this propulsion system for this PocketSat. I will say that it was quite a very amazing moment because we were developing, obviously we have been working in the development of the technology now for 2 years, but when we had this opportunity, basically because this other company told us like, hey, we have space for a propulsion system in our satellite, could you deliver a propulsion solution for this PocketSat in 2 months? And we were like, wow, no, so this is this is a huge challenge. Like, can we do it in 2 months? Obviously, the technology was almost ready, no, but it had never been integrated in a satellite before. So this was a huge amount of work. But our amazing team was completely on board, and we had a very, let's say, fun and crazy 2 months. In order to be able to deliver in time, but we did it, and now it's integrated, and we are waiting for the launch in January. So this is Athena Pie. Let me present you Athena Pie. It's our Athena version for PocketSats. You can see here the size of our thruster. It's very, very small. Here you can see actually the flight model, which has been integrated directly into the satellite. So these are at the bottom of the slide, you can see the specs, the data sheet of this Athena Pie propulsion solution. So it's, as I was saying before, it's actually less than 1 watt of total power. Thrust 30 micronewtons with a specific impulse of 3,800 seconds. Its total efficiency is 56%. I must say that this is the total efficiency of the whole system, not only of the thruster. So it takes into account also the losses of the power processing unit mainly. And it carried, this version carried 500 milligrams of propellant, of ionic liquid, which more or less it's like 200 hours of operation. So the total mass of the system was 90 grams. And you can see also let's see in the right part of the slide, you can see how the power processing unit looked like. You can imagine our electrical engineer when he needed to solve all these components. It was he's quite an expert now in soldering. That was also quite fun. And here at the bottom, you can see a propellant management unit, which is manufactured in titanium. It's a titanium deposits, and this basically the ionic liquid is held in this porous, let's say, reservoirs, no, made of titanium. So you can see the reservoir was only 3 millimeters thick, and in these 3 millimeters, it carried these 500 milligrams of ionic liquid. Okay, so here you can see in this picture how our thruster operated. I will run the video again. I will explain you now why the video is so short. You can see, first of all, at the right, I would like you to look at the right now. You can see how basically here is the current that is emitted from the thruster when we alternate the voltage. So basically we alternate between positive and negative voltage. So we extract these positive and negative ions. No? So you can see here how it operated, like this between these 200 and 300 micrograms of current in the positive and in the negative side. And this video, which I will play again, so you can see here, it has been recorded in our vacuum chamber. Normally we don't see anything, I must say, like electrospray technology, as I was saying, it's not the plasma. It doesn't have light when it's working properly, let's say. But here we had an issue with the vacuum chamber. We always record our tests, no? Because you never know. It's just one more diagnostic, no? And we are always recording. And in this occasion here, we had a problem with our vacuum chamber, and suddenly the pressure started to rise up, no? And we didn't realize that it was rising up. But suddenly we started showing this plume. I will play it again. which is actually the impact from the ions from the electrospray impacting with the background pressure, with the background air of the chamber, no? Because the pressure was too high, was not meant, this technology is not meant to operate with this pressure. But at the end, we had a very cool video that we can now play in all our presentations. But obviously this technology, as I say always, you cannot see you don't see a plasma plume because it's not plasma. No, what you are seeing in this video is just the air, the background air from the vacuum chamber. And then we need to qualify. And as I was saying, this was made only in 2 months. So it was a huge sprint we need to basically build the flight model, test it at our facilities and qualify it for flight. Here in this occasion, we qualify it at IDR here in Madrid. And basically what you need to do when you qualify this kind of systems, they need to pass both, let's say, the vibrations test and the thermal vacuum testing. No, here at the left, for instance, you can see how they vibrate. It was meant for the launcher in which we are going to integrate our propulsion systems. And basically the idea here is that they do they basically check what are the natural frequencies of your system. They perform this random load, which is similar to the launcher environment, and then they check again the natural frequencies, and they must stay in the same position, because if they shift more than 5%, normally they will tell you that something has broken and something has gone wrong in the test. No? So here you can see, for instance, the table with our natural frequencies, and the deviation before and after the test was less than 2% in all the natural frequencies. So this was very good news for us, obviously. And at the right, you can see the thermal vacuum test, which needed to go from -40 degrees to 80 degrees in 4 cycles. So we perform also these tests also at IDR, and then we obviously after this we perform functional tests to check that everything has worked correctly and nothing has gone wrong. No? Okay, so after qualifying, we need to integrate it with the satellite. Here you can see like in this picture the 2 PokeSats with our propulsion systems integrated already. This was just before we delivered them for flight, basically. So our requirements on the payload was that our envelope needed to be 40 × 40 × 30 millimeters. The orbit average power was less than 200 milliwatts, and the total mass of our system should be below 100 grams. No? So in terms of integration, we also need to take into account the power budget of the satellite, obviously, and the attitude control system, which is critical for propulsion. So here you can see how we managed or how we did the power budget analysis. So basically in this occasion, for this mission, for this particular mission, the total thruster power, as I was saying, is 1 watt. And we were going to do 6 firings of 30 seconds every 2 minutes, once per orbit. So we need to, let's say, program all the commands for our propulsion systems in order to comply with these requirements. And one of the issues that we had is that since the attitude control system of the satellites was passive, was not an active system, was directly done with permanent magnets, we could only fire when the satellite, we can only fire when the satellite is going to pass near the equator, because it's the only position, let's say, when the magnetic field vector is aligned with the velocity vector. So we need to also take into account this to program all the commands to the propulsion system. Also, in the attitude control, as I was saying, in this occasion is a passive attitude control system. And basically what, after all our simulations, by the way, we did with our own software. So we checked, obviously, let's say, the satellite providers with some simulations that they did in-house, but we performed also all our simulations with our own software to check that everything was going, that everything was correct. So here we saw that, for instance, that we need to wait 66 minutes until the satellite will more or less stabilize and we can start firing. No? So we need to wait. Once the satellite is going to be launched, we have this time that we can basically do anything. So what are we expecting from this first mission? Well, for us, obviously, it's about our first, let's say, IOD, which we expect to be able to, obviously, to ignite the thruster and to measure current and voltage, to measure all our performances in orbit. It's going to be let's say, a huge milestone for us as a company. we expect also to prove the operation of all our subsystems, of our propellant management unit, our power processing unit, and our thrust stack in space environment. But our commercial version in principle will be will be ready by the end of 2022. Here you can see, like in this graph, the mission duration as a function, let's say, of the amount of propellant that you carry. This also has been done with our own software. We have done simulations in-house. So basically, for instance, you can see if the launcher leaves you at 340 kilometers, if you don't carry any kind of propulsion system, the duration of your maneuver for this PocketSat will be like 25 days. Which is really, really low, no? If we carry with this Athena Pie that we have, as I said before, we carry 500 milligrams of propellant. In principle, the duration of the mission will increase to 75 days. So we are going to do a ×3 in the mission duration. This is our main goal for this mission. And if we would have more space, and we'll have been able to carry basically 10 grams of propellant, which was not the case for this mission, but maybe for a future one, we will be able to basically increase the mission duration to approximately 2.5 years. So really, propulsion, like I also was saying, it's not a nice to have. No, propulsion is completely critical, and for these satellites that are flying in so low lower Earth orbits, propulsion is completely critical if you want to stay more than 50 days in orbit. So also we have let's say our Athena Pie propulsion system will also fly in the Fosa Satellites, which is also a company here from a Spanish company, which they build Pico satellites. They are going to deploy a constellation of 80 PocketSats between this year and next year, in 2020. Sorry, between 2022 and 2023, and we have reached an agreement with them to basically incorporate all our propulsion systems in their satellites. But as I was saying, our main mission is not only to develop propulsion systems for PocketSats. Our technology is completely scalable. We have designed technology like this from the beginning. And what we expect is obviously to be able to incorporate this kind of propulsion in other different types of platforms, let's say larger platforms with different sizes, different shapes. This is one of the main, or let's say the strongest points of this technology. It's completely modular and it's completely scalable. So yeah, so I was saying, for us, we found the company like two years ago, and we have been working very hard to reach the point where we are at the moment. But we expect to really do, let's say, great things for the Spanish industry and from the European industry, and we expect to have our technology ready in order to incorporate our propulsion solutions in all the future constellations that are going to be deployed in the next years. So this was everything from my behalf. I hope that you enjoyed the talk, and if you have any kind of questions or anything you want to ask me, it will be a pleasure to answer them. Thank you.
Thanks a lot, Sara, for your presentation. It was really interesting. I was trying to read a bit the questions, but Mireia, you were following a bit the chat, and I don't think that people was asking too much, no?
Yeah, we have some comments about great presentations. Thank you for your interesting presentations, and congratulations for your achievements, and comments like that. First of all, thank you very much, Sara, for your time to be here today to share with us all your achievements, and for this fascinating presentation. For all the attendants, please feel free to write your questions on the chat, and we will answer them as soon as we have the opportunity. In the meantime, I have some questions. Okay. For example, we have a question: since you were a girl, you already knew what you would like to become, or is it something that has been not expected?
Thank you. No, thank you very much. Well, actually, when I to be honest, I don't remember the moment, the exact moment where I decided to be an aerospace engineer, since I think I've always wanted to be an aerospace engineer. Well, obviously, when I was a child, I was one of my dreams, as the dreams of, I will say, half of the people here in the world, was to be an astronaut. But I was always passionate about space, about engineering, and I always, like, when I started high school, I remember, like, for me it was very clear, I wanted to study aerospace engineer, and it was like, I wanted to do this, and this was my main goal. I always remember, like, also one of the things that, or one of the reasons why I think I really took this decision, was that when I was watching, let's say, the launches from Cabo Cañaveral, from Cape Cañaveral in Florida, when I was watching them on the TV, just when I was a child, I was just sitting there, watching the TV, I was like completely passionate about, like, everything. I was like, hey, I want to work there. I want to be in the mission control room with these people. Like, this was absolutely, so for me it was quite natural, like, to study this career, because I was, like, as I was saying, I don't remember the exact moment where I decided to study this.
Okay, we have two questions on the chat. The first one is about Fosa. You have talked about the collaboration that you have with them. I want to say, do you in January they will launch? They are going to launch 6 satellites. Is your propulsion on board of these satellites?
Well, actually, we are going to be launched in the same launcher. So we are going to be, let's say, we are going to be side to side with their satellites, but no, we are not carrying our propulsion systems in their satellites in this launch. Hopefully in the future, as I was saying, we have reached this agreement with them. But for this specific launch, no, we are going in other satellites. But it's fun because we are actually going in the same launch, so in the same right set, basically one side to side.
Okay, the success of the launch is your success.
Yeah, exactly.
Okay. Then there is also another question. Where do you think that electric propulsion will be in 10 years?
Wow, this is an interesting question. Thank you very much for the question. Actually, one of the greatest things about electric propulsion is that it's much more efficient than chemical propulsion. I think it's not that one is better than the other one. They are completely complementary. Like chemical propulsion is much more high thrust but less specific impulse, and electric propulsion in the other way around. I think in the future, actually, the combination of both is the most interesting solution, because with electric propulsion you can do, like, let's say you're going to have very high efficient maneuvers, which obviously for if you imagine, like, traveling to Mars, or traveling, like, deep space missions, with electric propulsion, basically you need to carry much less propellant mass, which is crucial for this kind of missions. But at the same time, for instance, for collision avoidance, it's more complex to do it with electric propulsion, because you need time for thrusting. Like, the thrust is much less, so you need more time to perform the same maneuver. So I think a combination of both will be where the future is going to be. But for electric propulsion, yeah, for instance, like deep space missions, like going to the other planets, going to asteroids, it's you can, I mean, the amount of mass that you save is basically exponential. So I think the future of electric propulsion is going in that direction.
Okay, thanks. There is another question that's a really cool product and very interesting presentation. Do you have any plans for on-orbit servicing? For example, refuel your propulsion system or something like that in orbit?
Well, really also interesting question. Yes, our main, let's say, our main mission at DNI Space is not only like to provide, let's say, thrusters for every satellite. No, this is not where we want to go. We actually want to provide any kind of, let's say, in-space propulsion. services. No? And obviously this could include as you were saying, this refueling the propulsion system in orbit, and any kind of let's say in space propulsion solution. So this is definitely the direction where we want to go, was maybe doing a space stack, manufacturing in orbit. We also know that NASA is considering the electrospray technology to print solar panels in orbit, which I think is a very, really cool application. So we can imagine like lots of different kind of applications. At the end, propulsion in space or in space propulsion is like having basically tools in space. No, it's like having the capability of moving, of maneuvering. So with this, you can do, I think, we can't imagine the amount of things that you can do with propulsion.
Okay, thank you. Okay, I don't know if there is another question. I need to check. Okay. Do you think that your career would have been easier if you were a man?
I don't think it would have been. I don't think it would have been easier. I do think that it's more difficult, like, to imagine yourself in a specific role if you don't have any references. And this is something that I think for girls not happens. Unfortunately, it still happens quite a lot. And for me, like, I didn't have these references when I was studying aerospace engineer, and this is sometimes, like, I imagine if, obviously now I think things are changing, because for instance LinkedIn, it's amazing, because in LinkedIn you can follow like lots, and the good, I mean, what I always say, like, this reference, they do exist, like they do exist, women that are doing amazing things in the space industry, no, but you just need to look for them.
This is exactly the thing that we are doing here, Sarah.
Yeah, exactly. So this is, I think this is the key, like, really, because it's very difficult, no, when you are a child and when you are studying at the high school, like, to imagine yourself as Elon Musk or as Steve Jobs, Mark Zuckerberg. They are all men, no, and it's really, really difficult. But I think, like, we should, let's use our social media, let's use the tools that we have nowadays to really, give visibility to, because they exist, no, these women that are doing amazing things. So I don't think my career will have been easier, to be honest, if I would have been a man. I can't say that I have been treated differently, like, I haven't, no, to be honest, I don't think, but I do think that maybe it would have been easier for me to imagine myself in a specific role if I would have been a man, no, for instance.
Yeah, congratulations, because it's not easy for us to find entrepreneurs in a main role in a company, to find a woman. It's something that we are looking for, and it's not easy. And people like you is really an example, a reference for not only young ladies, but also for the people in and outside a space career. Yeah. Okay, I have just 2 additional questions. Can you talk about some of the challenges that you face when you're setting up a new company?
Well, this is well, there are a lot of challenges that you face setting a new company, and in Spain particularly, I would say. But obviously one of the main challenges, when you want to build a company, that you want to do hardware, because obviously doing hardware is very expensive. Like, it's not just being with your laptop, no, at your home, building an app, doing space technology. It's very, very expensive, and obviously looking for money, I think, has been one of the greatest challenges that we had at the moment. I would say that I'm very lucky that I have, I think, me with my co-founders, we really make a very, very good team. Like, we met each other during our PhDs at the university, and we really worked great together. And I remember, like, the moment we took the decision to start the company was because we won a prize in a competition during our PhDs, and we realized that we actually worked great together. No, we were very creative. We had the same ideas, and we were willing to take the same risks. And this was one of the main reasons. But in terms of challenges, like, I will say, first of all, money. as I was saying, when you want to do hardware, you need funds. Second, that you need to build a very fast prototype in a very short, let's say, term, because if you want people to start believing that you can do something, you need to have built something fast, not have what they call an MVP, something that you can show, that you can demonstrate, because you need to demonstrate. At the end, it's not like, this is not the United States where maybe with a PowerPoint presentation you can raise $10 million. No, this, I think things doesn't work, or things don't work this way, not in Spain, definitely. So you need to demonstrate, and for this you need to ask for favors, you need to move all your contacts. Hey, can you manufacture this for me? Can you, because you don't have resources, no, at the beginning. So this is really, really hard. And obviously the administrative part also in Spain is particularly a little bit hard. You need to build everything in the right way from the beginning, I will say, because if not, you can get into some trouble.
Okay, I was muted. Okay, thank you very much. Now, in particular with you, that you're working in the new space economy, new space sector, how you value aerospace sector, both positive and negative, and the impact on the society?
How you can, sorry, can you repeat, because it was, I couldn't.
How you value the aerospace sector? How do you think that it could be a benefit? The benefits are the impact, the negative impact that could have on the society.
Well, there's a sentence from that we all always like to say from Dylan Taylor that says, like, we all are in the space industry, but we just don't know it yet. No. And I think that when people like think about the space industry, sometimes they think that we are just some freaks, that we are doing like weird stuff, no, like sending things to Mars or whatever, but they don't really, or it's difficult sometimes not to really tell people, hey, that in the space industry, like it's in all your daily, like how like, for instance, when you go to some place, not that you use the GPS from Google Maps or whatever, you are using technology from space. No, I think that it's really, I think that we need to do a more like this kind of events, no, and this kind of talks that are to really like make people realize how important is the technology that we are developing in the space industry. And one of the good things about the new space, particularly, is that it's allowing a lot of very small companies to really do a lot of innovation. And because it's not like, space is not just accessible for NASA and for ESA and from the Russian space agency, no? Now space is accessible for a lot of companies. And this is amazing because it's really, there are a lot of companies doing great things out there, like really doing innovative products and a lot of different applications. So I think it's really a very good moment to work in the space industry.
Absolutely. And last but not least question, which message do you want to transmit to the new generations?
Well, as I was saying, like, I think if at the end, I think you need to try to study something that, I mean, that you're really passionate about. I think passion is everything in life. And at the end, you're going to work, you're going to spend 8 hours or more per day working on something. No, you need to really study and work in something that you're passionate about. I always say, and particularly for the girls, something that they would like to say, you know, like try to be more like confident, like self-confident, because it's something that I really don't like when we are interviewing, for instance, people. No, we interview obviously men and women, and the girls, they are always like very shy, and they don't really, and they are. And when you look at their CVs and when you ask her like technical questions, they are very good, and sometimes they are even better than the guys, no? But they don't feel like, they don't have this confidence in themselves, and it's something that I always try to tell them, like, please, like, you are like, you have highest marks. You are able to answer the technical questions, so please be confident, like you can do it, no? But yeah, I think for the next generations, I always say, like, just follow your passions, because at the end, we are here to be happy, and so just follow your passions and don't think that you cannot do it, or maybe you're not going to be good enough. If you like it, you're going to be good enough at the end.
Okay, I think that now it's all. Thank you very much for your time, for your answer, for your inspiring presentation, and your reference to become a new reference in the Women in Aerospace. And you are always welcome to be part of our team and our network. And thank you very much for your work. Thank you.
Thank you very much, Mireia.
Thank you, everybody, to be here.
Thank you, Sara. I really like the last sentence that you mentioned it about being passionate and be confident, because it's something that we see with the girls, that they are really passionate, but the confidence is something that we are not. I don't know what happens to us, but we always feel a bit that we are not good enough, and it's really a good message what you did. So thanks a lot.
Thank you very much.
So let's finish here then the event, I think, for today. And we can wait that people disconnect for the presentation. And then if you want, Sara, we can stay with the group of WIA.
Okay.
And we talk a bit.
Okay, perfect.
Maybe we can stop the video also of the recording. Yeah.
Yeah, I just check it.